Okay. Uh, Welcome everyone to the third lecture. So yesterday we already started with block encodings, and today our goal will be to see what we can do with block encodings and how we can get block encodings. So I'll try to convince you that if you understand how to play around with block encodings, it's very easy to design a bunch of algorithms or many algorithms that maybe were like needed different ideas, sort of can be derived from a unified framework. So that's why people like this block encoding framework a lot, because it lets you get the unified treatment of quantum algorithms and unified way of thinking of why we have quantum speedups. And after that, I'll try to convince you that in some cases it's not completely crazy to assume that we have a block encoding. So I'll try to convince you that for certain matrices, I'll tell you how to get this block encoding so that you don't just think that I'm just hiding all the complexity in getting access to this object, the block encoding. But before that, let us just recall what a block encoding is. So, given a matrix A with a smaller equal than 1, a block encoding of A. Oh, sorry, this will be on n qubits. A is a unitary on n plus m qubits, such that 0 tensor identity is unitary U. But this is maybe it's the way you should think about it always is that we are given U such that we have A over here. We have something we don't know, something we don't know, and something we don't know over here. So it's easy to understand why we call this a block encoding of A, because, well, in a given block of this unitary matrix, we have A. So the name is sort of self-explanatory. And this is a very useful representation when we want to manipulate A on a quantum computer in a very efficient way. Okay, so let me just maybe explain another way you can understand this equation over here. This equation over here is telling us that if we start with a state that is the form psi 0, okay, then we can decompose it as something where we have A applied to psi 0 plus something orthogonal to this. So this bit over here is orthogonal. So in particular, if we measure, so if we apply U to psi 0 and measure the second register, yeah. Did I? Yeah, I guess the way I defined it here, yeah, sorry. I think probably it was wrong here. I should have. I think people usually did this. Sorry, I should have been more careful and copied it from my notes. But you're absolutely right, because I wanted. So yeah, so if we measure the second register, and I'm lucky enough to measure 0, the outcome is 0. The state of the system is given by a psi 0 normalized by. Okay. So in a way, if we have a block encoding, then conditioned on reobserving the 0 thing, we have a way of performing matrix multiplication with A, but on a quantum computer, right? So it's a bit of a different input model, and we're gonna output model, and we're gonna discuss this in more detail later, how this is different. And the probability of success is a psi squared, which will motivate the follow-up lecture, which is like, hey, we can then somehow only succeed in doing this operation with a certain probability. We don't particularly like that, of having like probabilistic things, but there is a subroutine called amplitude amplification that will allow us to somehow boost the part corresponding to 0, but this comes later. But just to say that later we'll discuss amplitude amplification, and we'll get rid of this probabilistic thing. Anyways, so this is again why we sort of like block encodings. It allows us to apply certain matrices. But you know, let's say you wanted to do some linear algebra, okay, and something that is very common, as we were explaining yesterday, is say you don't want to multiply the vector with A, but rather say A minus 1. Or something that is very natural for physics applications. Let's say you actually want to compute something like exponential of ITA. To do these things, you would want to not necessarily work with A, but with different powers of A, right? Because we could approximate these functions by, say, polynomials, and then try to apply them to a certain vector, and then do some linear algebra with them. So what we want in the end is not necessarily to work with A itself, but polynomials of A, or like any other basis of functions applied to A, so that we can approximate functions we want from this matrix and do linear algebra, design algorithms, and so on. And I'm going to explain to you now how to do this. So what is the idea? We want to approximate, let's say, polynomials of A, that is, get block encodings of polynomials of A to approximate other functions. And now, to make our lives a bit easier, I'll make one further assumption. Okay, so this assumption isn't really necessary, but we'll see later that it's fulfilled in many natural cases, and it just makes it's still kind of not the nicest computation ever, but it makes some computations easier. So what we're going to assume from now on, and again, this is not necessary, but makes life easier. We're gonna assume that u squared equals identity. Okay, so we do not only have the property that this is a block encoding, but we also have the property that when we take this block encoding and apply it to itself, we have something that is squares to the identity. So in this block encoding is actually a reflection, right? Because a unitary that we apply twice and we get the identity is just a reflection along a certain axis. Okay, so let me. So what do we get from this? So let's just define u to be. Oops. Okay, so in principle we don't really care what these R, L, and D are. Okay, but I'm just we only care about this particular corner of the matrix. I just want to show you what are the relations we get for these different parts of the matrix when we assume that u square is equal to the identity. So we'll all see now whether I can do matrix multiplications. It's not clear if I'll be able to do this live. So A, R, L, D, A, R, L, D. Let's just see what are the equations we get. We get that A squared, this is equal to A squared plus RL. Okay, and you know we can continue to compute the other things, but as far as I remember, these bits of the matrix won't matter as much. But what we know from this equation over here is that A square plus RL equals the identity. All right. Now I'm going to make another assumption, which isn't too crazy, at least in my opinion. We can implement identity. So essentially, as we're going to see later, this can be seen as some tensor product of like identities and one Pauli Z. So it's not too crazy to assume we can implement such a unitary matrix. This should be easy, but I'll just assume it for now. Okay, and then we can look at what happens when we do U identity. Oh, sorry. let's like U. I didn't give this matrix an A. Maybe I should. Let's call it V. U, V, U. So let's and then if you do this computation, okay, maybe I spare you the details, but essentially what you get is a squared minus RL. And well, what is the thing we observe? We know from the fact that a squared plus RL equals identity. We know actually what minus RL is. We know that minus RL is a squared minus identity. So we can simplify what is over here and write this thing as 2a squared minus identity, garbage, garbage, garbage. Why are we happy? Okay, so using this equation over here, we were able, and using this other v, we were able to get an expression for uvu such that the upper left corner doesn't depend on the garbage, right? It doesn't depend on R, doesn't depend on L. And this makes us very happy because we have an a squared and we have no garbage. So we see that by using this v once, okay, up here we have something that has a quadratic term in a and no garbage. And all we needed to do was intersperse u with this rather simple unitary over here. Okay, so if we want to get polynomial approximations of A, maybe a recipe like this one could work, right? We just keep interspersing U's and V's, and maybe if we're lucky enough, then indeed what we're going to get is like a matrix where on the upper left corner we have some polynomial of a certain degree of the matrix A, and something that doesn't depend on the garbage. And for those of you who maybe like approximation theory or something like that, maybe you already know, maybe already noticed that this is not any polynomial of degree 2. This is the degree 2 oh no, I got myself into a trap. I didn't write down Chebyshev on my notes. I never know how to write Chebyshev. There are like 50 different spellings. Didn't I write it over here? Okay, so sorry if I didn't write this correctly, but this is degree 2 Chebyshev polynomial. So the degree, So just as maybe a definition, a remark. So if you remark. The Chebyshev polynomials, they are defined recursively, namely tk plus 2 of x equals 2x tk minus, tk plus 1 minus tk of x, and t0 is of x is equal to 1, t1 of x is equal to x. So if you plug in k equals 0, you see you get tx squared minus 1, right? So what we have over there is precisely the Chebyshev polynomial of order 2. And they are a much better basis for polynomials. So if you look at this equation over here, it is not too difficult to see that the polynomial, like the Chebyshev polynomial of order k, has order, is a polynomial of degree, or let's say k plus 2 has order, has degree k plus 2, right? Because you always increase the degree by 1. So in particular, they are all linearly independent as in the space of polynomials. So we see that the Chebyshev, so like the set T0, T1, T D is a basis for polynomials of degree D. And it turns out that they are a much better basis than monomials. Another thing, so if you're doing approximation theory, for instance, for several functions, as we'll see in maybe like 1 hour or so, usually they're much better approximations in terms of Chebyshev polynomials than if you were using the more, let's say, vanilla basis of monomials. So usually, for instance, you can get approximations using Taylor expansion, right, which would be for monomials. But if you use the Chebyshev polynomials, you usually get something much better. And so yeah, the fact that we see a Chebyshev polynomial over there is actually good news, because it indicates that maybe we can also use some Chebyshev approximation magic later when we want to approximate things. And it turns out that this is indeed the case. So we have that the following holds. So fact. One can show that So it turns out that what I did over there generalizes. So if we instead repeated this procedure m times, no, I used k, yeah, k times, what would pop up on the upper left corner is the Chebyshev polynomial of degree k. The proof is tedious, so I decided not to do it in because I have to do a bunch of tedious calculations. But what you do is just you do it by induction plus you use the recursive definition of tk I just gave you over there. But yeah, so if you're interested, maybe we can or you can try, and if you fail, let's say try this afternoon. If you have questions, maybe we can discuss how to prove this tomorrow. I thought it was not really worth it to do it in full detail. But yeah, the point is we now see that using U and this matrix here, which we called V, k times, we indeed get a block encoding of tk of A. So using block encoding of A k times, we get a block encoding of a Chebyshev polynomial of order k of A. And yeah, I was using again this assumption over here, but yeah, that's not a too crazy one, as you'll see. Okay, so now I told you how to get starting from a block encoding of A. I told you how to get a block encoding of a Chebyshev polynomial of A. And these things form a basis for polynomials and are very good to approximate functions. So, well, basis. So the next natural thing we want to do is to be able to form linear combinations of the tk, right? So now that I've told you, let's say, so maybe we can erase this. So next step. So what is the next step? How to get a block encoding of sum alpha k tk applied to A. Because if we were able to get a block encoding of a linear combination, then we can start approximating functions, right? So this is a very natural next step. But before we do that, any questions on what we're doing, why it works, and or is it clear? All good? Great. So yesterday I already gave you some hints how we could, in principle, do linear combinations of things, and that is to, namely, add controlled versions of the unitary. Okay, so now, given unitaries u1 until ut, define a control big C control U to be the following unitary. So it will be sum t equals oh no, I started from 1 until t of tt tensor u I. Oh, sorry, ut. Okay. So what is this unitary doing? It is, you have two systems, right? One system which has log 2 big T qubits, and another system with n qubits. And this unitary is looking at the first system, and depending on what its state is, it's applying ut. But in matrix representation, this is just like a direct sum decomposition of these unitaries. So you have, like here you have u1, u2, u3 until ut. Okay. Now the next thing we're going to do is to consider the state on log 2t qubits given by okay, and why did I call this state f? Because these coefficients alpha t, they will be like these guys over here. So they will correspond to the different coefficient of the Chebyshev polynomials. Now, let us look at what happens if we consider the following state. If we do this, and then tensor identity, this control U, F, psi, this is equal to the state F sum alpha t ut psi. Okay. So What is this calculation telling us? This calculation is telling us that if we can somehow prepare this state, which is a superposition of various coefficients, then I can also prepare a state that is like a linear combination of these unitaries with these coefficients applied to the state psi. And I'm going to do this computation with you, but I guess we're getting near to the break. So I'll do the computation after the break, and first discuss what are the implications of this thing. So it follows that if we can prepare the unitary let's say Cu equals sum t equals 0 until the degree of t tensor uv to the power t, where this is again the block encoding, then I can get a block encoding of some alpha t, or sorry, alpha, did I also call it alpha t over there? Well, alpha k, sorry. Well, hopefully this doesn't cause too much confusion, but it will be, let's call it alpha k, tk of a. Oops. Okay, so this, I already, the reason for this is because these unitaries over here, right, if I showed you that if I apply this unitary m times to the state, then I'll get the Chebyshev polynomial, right? So each one of them will give me a block encoding of each degree Chebyshev polynomial, and everything is linear. So I can indeed just pull these coefficients alpha k inside of this block of the unitary. Okay. All right. Questions about this bit? Is it clear why we are happy? So again, we now can do linear combinations of these functions, of these polynomials that are very good to approximate things. So if we pick the alpha k's in a smart way, we'll be able to approximate various functions of A. We concluded that if we believe that statement over there, then I've given you a recipe of how to do block encodings of linear combinations of Chebyshev polynomials. Okay, so let's just finish and do that computation over there. It's hopefully not too difficult. So let's just, the first thing we're gonna, so proof of let's give this identity over here a name. Proof of 1. So the first thing we're going to do is just apply this big control unitary to f and psi. So let's see how this guy looks like. Well, this would be this big control u. Oh, should have given me some space here. By linearity, this is just this big control u, sum over t, alpha t, control u, t, psi. Because, well, you know, this is just the, this is just the definition of f, right? I can expand it in this basis like this. Now, this cu has a very special structure. When it sees a t on the first system, it just applies the unitary ut to the second one. So we know exactly what this guy does, right? So this will just be sum t square root alpha t. Nothing happens over here, and over here we have a psi. And this is the same. Yeah, no, let's leave it like this for now. Okay, good. Now, what we need to do is to compute this projection over here, right? So, what is now f tensor identity on sum t square root alpha t t ut psi. Let us expand this guy now. So this is the same as f, and then sum square root alpha t t. This is just this vector over here, right? Tensor identity. And this whole thing will multiply this thing. Okay. Now, let's finish the computation. So these t's over here, I should do a t prime so that we don't get confused. So these t primes, they are all orthogonal to each other. So when I hit this thing with this thing over here, the only term that is non-zero is when t prime equals t, right? So, and then I have to sum over all t primes and t. And then when t prime is equal to t, I'll get these two together. So we see that what we get is f and then sum alpha t u p psi. Because again, this thing is only non-zero when they are the same, so that's where the alpha t is coming from. And on the second system, I'll always get an f. So that's why you have an f over here. So we've shown this identity over here. And what is this saying from an operational perspective? Well, so if I sort of start, if I can prepare this, so prepare this state f, and I can implement this controlled unitary, then if I measure f again on the first register, then I will have prepared this this state over here. Oh, sorry, this state over here on the second register. Right? So what do we learn? Okay. So what do we learn? So what power have I given you now? So we see that if we can start from a block encoding of A, and then in principle I have only showed you how to do it with u squared equals 1 identity. Suppose we have unitary, let's call it W, such that W0 equals F. Now, suppose we sorry, I forgot this bit. A controlled block encoding of A. Then it follows we can get a block encoding of some alpha k tk a with from k equals 0 until d with d plus 1 uses of the block encoding of A. Okay. And this is very useful because it essentially it tells you that if you want to approximate a function of degree d, a polynomial of degree d, if I give you such a block encoding and you can produce the state f, then I only have to use this block encoding d plus 1 times, and I'm able to do this to obtain this polynomial of the matrix. In particular, if having this block encoding isn't too expensive, then we are performing manipulations of matrices which are huge, right? I mean, A is an n-qubit matrix, so it's a 2n by 2n matrix. And I'm telling you that by just like applying this unitary U, a few times, you can apply polynomials to this matrix with a number of uses of u that is independent of the dimension of this matrix. Okay, so this is highly non-trivial, right? I mean, again, this is a 2n by 2n matrix. And if, let's say, on a quantum computer, you can do this relatively cheaply, okay, then you can do this relatively cheaply. And this is amazing, okay? So, because again, as we're going to see in a few minutes, being able to get polynomial, like Chebyshev approximations of a matrix allows us to approximate various functions of interest. So, is it clear that this is powerful? Okay. Right. Very good question. So, so Ruben's question is a very important one, and I should have anticipated it. So, what is so essentially, it's if you look, so Ruben's question was the following one, like in order to be able to do this, right, to implement this thing, I need to be able to measure f when we do the after we apply this thing, right? And then it's not. So what is the success probability of that happening? Well, it's just the norm of this vector over here, right? Do you agree? So the success. So remark. The success probability of measuring f is the norm of this thing. Sorry, with the alphas, yeah. So as long as you're applying your blocking, I mean, as long as this function of the matrix doesn't really kill the psi too much, then you're fine. But again, it's not nice to only be able to do something probabilistically, because let's say if you want to repeat it many times and you need it to succeed every time, then suddenly your probability of success starts to decay exponentially and so on. So later we're gonna see this trick called amplitude amplification, which allows us to get rid of this probabilistic component of the algorithm by having to do more operations on the quantum computer. Okay. Mm-hmm. Mm-hmm. Right. Okay. So Mika is making the very valid point that I was sort of lying, but for instance, so why was I lying? I told you that if implementing this is cheap, then you only need to do like d+1 uses of the block encoding to approximate this thing. But for most problems you care about, usually the degree of the approximation will scale with the underlying dimension. So the number of uses will in the end scale with the size of the matrix. And also, as we're going to see in the second part, it is essentially never the case that the cost of implementing one of the use is independent of the dimension. So essentially, I'm hiding a bunch of costs here, right? Because usually the degree of the approximation will scale with the size of the problem, and the degree or like the cost to implement this will also scale with the size of the problem. But so when do we have really good quantum algorithms? Well, the answer is right there, right? I mean, if this degree only scales mildly with the dimension of the problem, then we're happy. And if the cost of implementing this also only scales mildly with the dimension of the problem. So if like generating a block encoding of A doesn't take something that is, let's say, a polynomial of the dimension of A, again, this is a 2n by 2n matrix, right? Let's say it's only polylog on A, then this bit is cheap. And if the degree of the approximation also only scales, let's say, polylog in the dimension, then we're also happy. So I was not planning on being dishonest today and tomorrow. I was just being dishonest now to see if I can amaze you a bit. Indeed, there are like lots of hidden costs in this step and in this step. And later we're going to discuss exactly both the cost of getting this and the cost of the approximation for various problems. Okay. But what is nice is also the high level perspective of this framework, right? Because if you want to design a good quantum algorithm, I've told you what are the two things you need to do. You need to get me a block encoding. This is like the quantum part. You need to be smart and be like, hey, like for these classes of matrices I care about, I can design such a block encoding in a smart way. And the second bit, which in principle has nothing to do with quantum, but if you go into like more recent papers on quantum algorithms and so on, you see that the second thing you need are very good approximations of the functions you care about. And in principle, this has nothing to do with quantum. This is purely like classical theory of approximations. And if you have these two ingredients, good block encodings, good approximations to functions, you have a good quantum algorithm. Okay. All right. So as I mentioned, the plan is now to discuss this for some cases, and then later this for some more explicit cases. But before that, I just wanted to write down a theorem, which is a bit more general, just for you to have seen it at some moment in time, because I think it's important. So the reason I wanna write it down is because I only showed you how to do the Chebyshevs, and I had this assumption over here. But maybe you want to do, you're more comfortable with monomials, and let's say for the problem you care about, you only have a block encoding, you don't have this assumption. So I just wanted to write down the more general version. So, and this is by Andras Gillen et al. So we let P from -1, 1 to the complex numbers that have absolute value at most 1/4. So it's not any polynomial, you have to normalize it properly. Be a degree D polynomial. And, oh, why did I capitalize it? And, how is it called? U, a, n, plus m qubit block encoding of A. Then we can implement a O n plus m plus d qubit block encoding of P applied to A using order D applications of U and U dagger, one controlled U and all of the other 2-qubit gates. So this is somehow, let's say, the mother theorem for these things, right? Because it tells you that as long as you know you have a polynomial that is bounded, on the interval that to the complex plane that is bounded, then and you have a block encoding. Note that I'm not making anymore the assumption that it squares through the identity, so it's a bit more general. But now I'm also assuming that I can implement both U and U dagger. Okay, so it's slightly different, right? But I'm telling you that then I can get a block encoding of the polynomial applied to the matrix, and the number of applications is the same as before. It scales linearly with the degree of the polynomial, and you need also order degree of the polynomial order 2-qubit gates, and this essentially comes from like having to prepare a state like F. Okay. And maybe just one remark. In practice, this bit over here is a bit annoying, right? To check. Maybe you're like, oh, like is my polynomial indeed between at most 1/4? So just another remark, which is if you're given a polynomial in the Chebyshev basis, so there's another representation of the Chebyshev polynomials, which is given by tk of x equals arc cosine of cosine kx. And using this, you can, this is just an other definition of Chebyshev. And from this, one can show, I mean, the arc cosine, right, is a bounded function, right? So if you have, using this definition, it is sort of not, it is easier to control in terms of the alpha k, what is the range of the polynomial if you're given it in Chebyshev basis. So just a remark here. Okay, so yeah, this is a general theorem that tells you exactly what you can do with a block encoding in a degree D polynomial approximation. Okay, so we can now follow two routes so the next two things we need to do are obvious, hopefully. First, explain how to get good block encodings, and second, for which problems we have good approximations. These things are sort of independent, and I was wondering, first I was thinking I was going to do this first, but I was thinking that maybe this part is a bit more exciting / interesting, so it might be nicer to first see applications and then do more theory. But yeah, I'm now divided. So any remarks? Do you prefer to first see how you get block encodings, or do you prefer to first see applications? Any preferences? No. The second? Okay, I heard second somewhere. So let's do applications. So for now, you're still going to have to assume that there is this magical being that gives us a block encoding, and from there, our lives are good and easy. And then later, I'm going to explain in which situations that you can assume that there is this benevolent being that gives you a block encoding without someone telling you you're crazy. All right. So let's do quantum linear system solvers. So this problem has already some history. So the first algorithms were by so-called HHL, which stands for Harrow, Hassin. I'm being recorded. I should have written down how to write the names of people properly. I'm not so sure it's spelled like this, sorry. And Lloyd. So they were the first ones to consider how to use quantum computers to solve linear systems of equations. But now I would say that it's much better to take a look at how one would do it in this block encoding framework, because it's much simpler than what they do if you've already digested that bit. Okay, and solving systems of equations is, of course, a very, 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 very fundamental problem that pops up all the time. So maybe it's like one in the top 5 on most important problems in computing. So but you're going to do it on a quantum computer. So first I have to tell you what it means to solve a linear system of equations on a quantum computer. So this is the what is known as QLSP, which stands for Quantum Linear Systems Problem. And what is this problem? So we are given some A, which is an n-qubit matrix. We assume for convenience it's Hermitian, but it's not too important to assume that. Such that the operator norm of A is smaller than 1. And some vector B on C2 to the n and some epsilon greater than 0. The task is to prepare a n-qubit state x bar such that the norm between x bar minus x is smaller or equal than epsilon for ax equals b. All right, let's digest this a bit. Now, first, I'm making these assumptions over here are normalization assumptions. But what is very important here is the way the output and input of the problem are defined. So when we solve a linear system of equations on a computer, let's say you take MATLAB and you use it to solve this equation over here, what it's usually outputting is like just some list x bar, right? So on a classical computer, you usually given x bar as a vector in a memory. Here, I'm asking you to prepare me a quantum state that is proportional to the thing we want, right? And this is a much weaker assumption, right? Because here we have a quantum state which is approximately equal to a minus 1 b. So it's there lying on a quantum computer, and for instance, if you ask me, oh, what is the second entry of x? Here, I can just look at the second entry in my memory and tell you. Here, I have this quantum state, right? So I just have like some x equals some alpha I stored in my memory and in my quantum computer, right? And in principle, for instance, I can measure it, I can use it to then do other quantum algorithms with it and so on, but it's not so obvious, for instance, how to get go from this representation to this representation over here. Okay, but it's very important to understand that when we are solving this problem, it's not directly comparable to solving the classical problem. Okay, and sometimes this can be to our advantage, because we're going to see how to solve in time O poly n under some assumptions. On A. I'm going to discuss in a few seconds. But this is sort of crazy, right? Because we have a 2n by 2n matrix, and I'm telling you that I can solve this problem in a time that is like polylogarithmic in the dimension. It's impossible to solve this problem in this time. Can someone tell me why? Like, what is a lower bound? What is something, if I have the solution as a vector in a memory, what is something I have to do? I have to write what is the component of each thing, right? And just to write down a vector in this space, it takes me this time. Okay, so we see that what we're doing here is fundamentally different. Okay, but let's say if your application also works, if you're given the output of the linear system solver as a quantum state, and frankly, we don't have that many, let's say, end-to-end applications where all the assumptions are satisfied and this sort of output is sufficient, then you can, in principle, have exponential speedups compared to classical methods to solve linear systems. So, as someone in the audience remarked, I made a mistake here, so sorry about that. So this is wrong. I switched the order of the arc and the cos. Sorry about that. So the correct, I mean, if you just go to Wikipedia, you see that the definition they have is this one. So the Chebyshev polynomial satisfies that the kth Chebyshev applied to cosine is cosine k cosine theta is cosine k theta. I think actually this representation is even nice. I mean, this is the defining relation, and this representation is even nicer because from this you can immediately see. I mean, this thing here will have range minus 1, 1, right? And then you see that if you feed the Chebyshev polynomial something that will have range minus 1, 1, you get something that has range minus 1, 1, right? And what should be said is when you look down at the expansion of the Chebyshev polynomials in the monomial basis, I mean, recall that hopefully I won't mess things up again, but tk of x, you can define it recursively as 2 tk minus 2x, tk minus 1 minus tk minus 2x. And note that we always have this 2 over here, right? So in particular, the term of order x to the k will have a 2 to the k in front of it, right? So we keep doubling. So the coefficients of the Chebyshev polynomial, when you expand them in the monomial basis, they are quite crazy. That's why if you look at it at first, you're like, oh, this takes very high values, but from this representation, it then becomes clear it does not. And it's super important actually that the Chebyshev polynomial behaves crazy in the monomial basis, because actually what did I want to say? Yeah, if they were very well behaved in the monomial basis, they would more or less be the monomials up to some small linear transformation. So the fact that they're qualitatively different is reflected in these coefficients. So thanks for correcting me on that. All right. So we discussed what this quantum linear system solver problem is, and the thing we have to now make some assumptions on how we get access to A and B, right? Because if I don't make assumptions on how I have access to A and B, then it's impossible to solve this problem. So what are we going to assume? Well, for how we're going to have access to A, that should come as no surprise, because what do I want? What is the assumption? Have access to A as block encoding U, can also implement U dagger and controlled U. Why am I making these assumptions? I want to play with this, right? And this is what that theorem requires. So one, it's going to be this. Assumption number 2 is that we can prepare B as a quantum state. So this means, i.e., I have a unitary W such that W applied to 0 is equal to B. And maybe you can erase my mistake so I can be less embarrassed and keep the theorem. So assumption 1 and 2, I would say, are not so controversial. I mean, if I want to have very large speedups for this huge matrix, like if I want to have a huge speedup in the way I can process this huge matrix, then I must be given it in some very nice form, right? There's no way. Like this block encoding assumption I can live with. Also, if you want to sort of solve a linear system described by B, then I sort of buy it that you need to have a way of having quantum access to B. And now comes, well, maybe I can comment on this later. Now comes a more controversial one. So we're going to assume A is well conditioned. Namely, that the eigenvalues of A are in -1, -1 over kappa, 1 over kappa 1 for some known kappa. Okay, so why is this controversial? Well, if it's not so easy to control the eigenvalues of matrices, right? So I need to apply this, right? This is an input of the algorithm. If I don't have this, then in principle I cannot do the magic I'm gonna do now. So I am given this huge matrix, and I'm assuming that through some magic I have some very fine control over the eigenvalues of A. And I know that this system is very nice, because the closer, like the further away the eigenvalues are from 0, the easier it is to invert matrix, okay? And in many applications, let's say, for instance, if you're solving differential equations with finite element methods or whatever, the art is really to reduce the problem to solving a linear system of equations that is very well conditioned. Okay, so if you want to use this in practice, you not only need to find me a good way of preparing this B and this block encoding, but you need to make sure that the system is well conditioned and you know how well conditioned it is. Okay, so this is important. Okay, so maybe one remark before we solve the problem. What is the function we are trying to implement of A? So if we want to solve a system of equations for a Hermitian matrix, so what do we want? We want to apply the transformation A minus 1 to B. So if I have a block encoding of A minus 1, then I'm done. Because then, as we were discussing before, if we apply this block encoding to something of the form B0, let's call this, let's say, U inverse. If we apply this U inverse, we'll get something which is like A minus 1 B0 plus some garbage that is perpendicular. And then, in principle, if we measure 0 in the second register, we have solved our problem. So, does everybody agree that if we had a block encoding of this matrix, we would be happy? All right. But the issue here is that the function x goes to 1 over x is not a polynomial. Okay? Not, I think, should be immediately clear to everyone. So, to get a quantum algorithm that solves this, what is the only thing I need to do? I need to be able to approximate this thing by a polynomial. So the quantum part of designing the algorithm is done. All the quantum part of designing this fundamental quantum algorithm was sort of relegated to making sure that we have this block encoding and that we can play with it, and that we can have a block encoding of B. And this was all of it. The rest now is only about like approximating functions. And to get a polynomial approximation of the inverse function, we will use this thing over here, because the 1 over x function is very well behaved as long as you're not too close to 0, right? And this is precisely where we're going to use this assumption to get a good polynomial approximation of the inverse function. And then we're done, right? So you could, so here's our good polynomial approximation. So here's a lemma. Let pk of x be equal to 1 over x minus 1 minus x squared to the k. Then for 1 over kappa smaller equal 1 absolute value of x smaller equal 1, we have pk of x minus 1 over x is smaller equal epsilon, yeah, epsilon. Is that it? Right. Of course, that's why I was confused. I'm missing for k equals order kappa. Oh, it was a very bad idea to use k and kappa at the same time. So let's do L. Sorry, for L equals kappa squared log kappa over epsilon. Now, some remarks. Why is this a polynomial? Well, we have the x squared here. So if you see that, the term corresponding to 1 will cancel out, right, when we expand this in L. And all the other terms will have at least an x squared. And then if we divide it by x, this is a polynomial, right? So just before we prove it, just some remarks. So this is a polynomial. So PL is a polynomial of degree order L. And what is the intuition going on over here? Why you could have come up with this polynomial approximation of 1 over x? Well, we are not happy with so if we didn't have this part over here, then we would be super happy, right? Because this is just 1 over x. And what is the intuition here? If we take x that is far away enough from 0, this will be like some number between 1, like that is far away from 1. So if you, let me write it down. So for, let's say if you have x larger than 0, but at most 1, then 1 minus x squared to the L will be exponentially decaying in L, right? So as long as you're far away from 0, this term over here will decay exponentially in L everywhere. So we can essentially ignore it. So that's why this is a good polynomial approximation to 1 over x. And this is how you come up with it. And actually the proof is exactly that. This is also how we prove that this is a good approximation. So proof for as long as we have this, we have 1 minus x squared to the L is smaller equal, I mean, the worst point we can pick, like for which this will decay the slowest, will be the point that is the closest to 0, right? So this will be at most minus kappa to the minus 2 to the L. And now let us write this. Let us use our bound for L. So this will be 1 minus kappa minus 2, some constant, kappa squared, log kappa over epsilon. Now, this thing, like 1 minus kappa minus 2 to the power kappa 2, if you do this thing, as kappa goes to 0, this will be like order E, right? So this will be smaller equal E to some C prime log kappa over epsilon. And then what you get is that this whole thing, that 1 minus x squared to the L is smaller equal epsilon over kappa for like C and C prime appropriately chosen. Just some constants. And then, you know, what do we do next? We just see that 1 minus x squared to the L over x minus 1 over x. This is 1 minus x squared to the L over x. Here we use the fact that we use our bound, right? We use that this is at most epsilon over kappa. So this will be epsilon over kappa times 1 over x. And then here, again, we need to say how close we are at 0 to 0. This is what will tell us whether this will explode or not. So we again use the fact that we have this assumption, which will cancel out this kappa. So this is smaller. Everybody agrees? All right. So you can also show. So let's say another lemma. This is probably it's essentially the same proof. It's a bit tedious. You can show that PL of x is at most what do you want to say? Yeah, is at most kappa. Okay, so again, okay, so here is if you want, here is this proof for this, which is obvious. This function here, the 1 over x is at most kappa on this interval, right? And we know that this guy here is epsilon close, so it can be at most kappa plus epsilon. But you can refine the analysis a little bit. So the kappa plus epsilon we already showed, but you can actually show that this holds. So it follows that PL of x over 4 kappa satisfies the assumptions of the block encoding theorem. And, well, this gives us a quantum algorithm to solve linear systems. What is the scaling? So I can implement block encoding of PL of A over 4 kappa with OL uses of the block encoding of A. So this thing is what? I told you what the degree is. It was kappa squared log k over kappa. No, this is ugly. And we showed that PL of A over 4 kappa is essentially A minus 1 times 4 kappa, right? And we're done, right? Because I showed you how starting from a block encoding of A with these and U dagger and so on, how to then invert this matrix. And how many times did we have to use the block encoding of A? Something that scales quadratically with the condition number. Okay, so there's no dimension here. There's only the condition number, which is crazy, right? So in principle, the number of uses of the block encoding is independent of the dimension. You just have to have a very good condition number. But again, the devil is in the details, right? Because first, there is the scaling with the precision. So if we want the high precision, let's say precision that scales with the dimension, then the number of block encodings will also increase accordingly. But it's a log scaling, so it's not the end of the world. And generally speaking, if you're looking at a most linear systems of equations, this condition number will not be so well behaved. So this will only be super good if the condition number is also polylogarithmic in the dimension. Okay. All right. So what else? So one remark. The analysis can be improved to yield L equals O kappa log epsilon. So if you are a bit more careful with this approximation over here, then you can actually improve the number of the degree quadratically, okay, in the block encoding. But the proof is a bit more tedious. This one is nice and easy, so that's why I presented this one. And yeah, what are some other comments one should make? So I already told you the block encoding, the input, and so on. So yeah, maybe one important comment is that there are also classical solvers that, like on a classical computer, whose scaling only depends on the condition number times something depending on the size of the matrix. Okay, so if you want to solve a linear system of equations classically, there are also solvers where the relevant parameter for the scaling is given by the condition number, but they all have at some point to do some sort of matrix vector multiplication or whatever, and then you already have some linear scaling in the dimension or something scaling with the sparsity, which is something we're going to discuss next. So this indeed gives a very large speed up. And yeah, I think that was essentially all I wanted to say about the linear system solvers, unless there's some questions. No? Yeah. Uh-huh. Mm-hmm. 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 Okay, so just maybe this is actually a subtle point I forgot to mention, which is very important. So thank you for your question. So okay, I already erased the statement of the problem we're solving, but in the statement, I was making the assumption that the norm of A is at most 1, right? So, well, when I was saying about the condition number, I was also making this assumption explicitly. And as Mika was saying, we have 2 to the n eigenvalues. Okay? And I'm saying that all of these 2 to the n eigenvalues, they are squeezed into this interval, right? And so the typical distance between these eigenvalues will also be like 2 to the minus n. Because, I have to pick of order 2 to the minus n, right? Because I have to spread out 2 to the n numbers, unless your system is like super degenerate and you have like a lot of degeneracies. You have to spread out all of these eigenvalues into this very small space. So they have to be very close to each other to fit them all. And yeah, so in principle, so this normalization really makes me squeeze all eigenvalues together. And Mika's question was like, hey, does this also mean I have to have an exponential precision in the way I implement the thing? And my answer would be 2, would be like, I would split it in 2. The first part is where, so let's say you start with some matrix, okay? Let's say you start with some matrix A prime, and then you normalize it to get something like this. So if A prime, the matrix you start with, indeed has some operator norm that is, let's say, scaling with a polynomial in the dimension, right? Then, indeed, you would require a lot of precision in order to go back, right, from A to A prime. But the scaling in precision will be logarithmic. So that should be fine. And also when you implement, usually when you implement the block encoding, you can get like a dependence in the precision that is also polylogarithmic. So this will not kill you. But if you have it's very artificial, in my opinion, to then, if you have the largest eigenvalue to be poly n, to then also assume that the condition number will be very well behaved, right? Because if I want, like, after dividing by 2 to the n, that the eigenvalues are not too far away from 0, then somehow you have to have a matrix such that, like, most of the eigenvalues are of order 2 to the n. Otherwise, you have like exponentially small things after you normalize. And then, if you look at the scaling in condition number and not precision, then it's polynomial. So unless you have a matrix where most of, like, let's say in this case, where most of the eigenvalues are indeed of order like A prime, then once you and you have A prime of this form, once you normalize, you're lost. So the answer is, I think that the precision itself is not what kills you. I think what does make it a bit stupid is the fact that you have to make some assumptions on the eigenvalues which are very, very, very strong. Okay. So, okay, great. Yeah. But so that bit. So we're gonna see later that I guess. Okay, we have 15 minutes, so we're gonna see tomorrow that under some like, I think that the scaling and the precision to build U will be polylogarithmic and epsilon. So even if you want to take like implement U up to exponential precision, the overhead will be okay. But I think this is something a bit more annoying. So why are we having all of these contrived discussions, and why are we saying all of this? Because, you know, we already saw an example here, right? Because like at first when you look at this, you're like, wow, this is amazing. No scaling in the dimension, only the condition number, and like linear systems are everywhere. So quantum computers are gonna be able to solve everything much faster. And we have to be careful, okay? Because we're making a lot of assumptions. Some of them are super generous. For instance, look the discussion we just had, right? If you start looking at use cases, you see that it's very hard to make sure that this all works as we want it, okay? So even though this is super interesting, in my opinion at least, and non-trivial, you have to be careful, because the assumptions we're making are very restrictive. And so people like to say that when you see results like this one, you should always read the fine print. And when you try to apply it to, let's say, real-world problems, it's then a bit tricky to fiddle with all of this. Okay, other remarks, questions about this? No, I think the original HHL didn't have log scaling and precision. I think the original HHL didn't have log scaling in the precision. So I think this is better. I think this is more or less state of the art, yeah. Yeah. Did I say? Do you disagree, or maybe I'm misremembering? I mean, I'll check for tomorrow if I'm saying something stupid. But I think that at least the original paper of HHL had a polynomial scaling in epsilon, but I'm not 100% sure. Other questions? Okay, then I guess we have 10 minutes. So let me just, before mentioning how to construct it doesn't make sense to start explaining how you construct these things, these block encodings. So I'm just gonna mention one more application that is almost immediate from what we had today, which is that of Hamiltonian simulation. So I think this is actually much more solid than HHL. I think this is really like end-to-end. So it should be mentioned, and although it's more physicsy. So you're right? Okay, good. Good. Okay, so just maybe some last comment about for today, for the physicist, Hamiltonian simulation. So one thing that is this very natural to try to do with a quantum computer is like given A, which I'll now replace by H because it's so-called a Hamiltonian in physics, and some T and R we wish to implement EITH, and again assuming that the norm of H is more than H1. So this is a very important problem in physics because it describes the time evolution of quantum systems. And how do we get Hamiltonian evolution? How do we, also this is a unitary, right? Something that should be mentioned. So it's not too crazy to think that a quantum computer could implement such unitaries. And here's a fact. There exists a polynomial approximation of e to the itx of degree up to epsilon of degree t plus log epsilon plus 1. So from this, we immediately obtain that if we have a block encoding of H, then we can obtain a block encoding of e to the iht with O t plus log epsilon minus 1 uses. Now, and this is essentially also, there is this whole field devoted to Hamiltonian simulation. So like there's this non-trivial fraction of the community that is exclusively dedicated to approximating these things. So this is hugely important. But this is already essentially optimal. Okay, so essentially we see that again with this block encoding machinery, all we needed to do to solve this fundamental problem in simulation of quantum systems was to get ourselves a nice approximation, polynomial approximation of a function, nothing quantum there, right? And then we get a super powerful algorithm. And I think this is a much more well-motivated, whereas here I was saying like, oh, there is this caveat, and then the audience came up with other caveats and blah, blah, blah. I think this is much more solid because for physical systems, before you normalize, indeed it is usually the case that let's call the H prime, the one you have before normalization, then this usually scales like a polynomial in system size. So after you normalize, so all you would have to, you would have to put a polynomial in T here after you normalize, right? So the factors I'm hiding here using the normalization, it's okay to argue that they should be of polynomial in n size. Whereas for linear systems, it's not so clear, right? And tomorrow, the first thing we're going to see is that for these ages that come from physical systems, there is a clear recipe how to get a very efficient block encoding of them. So also this part is not crazy to assume. So I think this application is much easier to defend than that one. But just to finish, I know I've said this like 50 times already, but just one last time. Why are we super happy with this block encoding and polynomial approximation framework? In order to I start from a block encoding. You tell me the linear algebra problem you want to do. Let's say, in this case, exponentials of matrices. You go to your favorite book on approximation theory of functions. You find a good polynomial approximation, and you have an algorithm. This is a very nice and powerful workflow. It really simplifies the problem of understanding quantum algorithms and also how to get better quantum algorithms. How do you get better quantum algorithms? You find better block encodings. You find better approximations. I mean, of course, there are billions of other tricks. This is very reductionist, but at least for the fundamental problems, this actually gets you quite far. All right. So tomorrow, as I said, we're going to see how to actually get certain block encodings. And if time permits, we'll also discuss this amplitude amplification procedure, because so far we've only seen how to, after you obtain the block encoding, getting the state you want probabilistically. We'll see how to change that. Right. Okay, thanks. See you tomorrow for the last lecture. Sorry, the usual question. Any feedback, questions, desires for tomorrow? I mean, anything you'd like to see in the last lecture?